Light is the fastest thing in the universe. Nothing with mass can reach it. Nothing with information can exceed it. Einstein derived it. Every particle accelerator confirms it. Every experiment in the history of physics has failed to find an exception. The speed of light is 299,792 kilometers per second, and it is the hardest ceiling physics has ever identified. Except for one thing. Space has no speed limit, and right now it is using that freedom to erase the universe. That sentence requires a distinction that physics education almost never makes. Einstein's speed limit applies to objects moving through space, a ship, a particle, a photon. Anything traveling through space as a medium is subject to the limit, but space itself is not an object moving through anything. Space is the medium, and the medium has been expanding since the Big Bang, carrying everything in it along for the ride. When space expands, the galaxies embedded in it are not moving through space at all. They are stationary relative to their local surroundings. The space between them and us is simply getting larger. That is not a technicality. It is the difference between a rule and the medium the rule operates within. The rubber band makes this exact. Draw two dots on a rubber band. Stretch it. The dots move apart. Neither dot traveled along the rubber band. Neither one accelerated, neither one broke any limit. The rubber band itself got longer, and the dots separated as a consequence. Now imagine stretching that rubber band faster and faster. At some point, the dots are separating faster than you could ever crawl along the rubber band's surface. No speed of crawling helps. The rubber band is expanding faster than the crawl can compensate, and the gap grows without bound. The dots are not moving. The surface is. That is the universe. The galaxies are the dots. Space is the rubber band. The expansion of space has been happening since the first fraction of a second after the Big Bang. For most of cosmic history, the expansion was decelerating. The mutual gravitational attraction of all matter was pulling back against the initial spread, slowing it down. The expectation for most of the 20th century was that gravity would eventually win. The expansion would halt, possibly reverse. In 1998, two independent teams of astronomers were measuring the brightness of distant Type 1a supernovae. Type 1a supernovae are useful cosmological tools because they explode at nearly the same intrinsic brightness. They are standard candles. By comparing how bright they appear from Earth to how bright they should be, you can calculate how far away they are. Both teams found the same thing independently. The Supernova Cosmology project, led by Saul Perlmutter, the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. The distant supernovae were dimmer than expected, not brighter, dimmer. Dimmer means farther than predicted. Farther means the universe had expanded more than gravity should have allowed. The expansion was not slowing down, it was speeding up. Both teams spent months checking for errors. Both teams published anyway. The discovery overturned the dominant cosmological model completely and earned the 2011 Nobel Prize in Physics. The force driving the acceleration was named dark energy. Nobody knows what it is. It constitutes approximately 68% of the total energy content of the universe. It is the dominant component of everything that exists, and it is making the expansion faster with every passing second. The expansion of space operates differently at different scales, and this is where the intuition gets repaired. At the scale of a room, a city, a solar system, even a galaxy, gravity dominates. The mutual attraction of matter at these scales is strong enough to hold things together, to prevent local expansion from pulling them apart. The Andromeda Galaxy is 2.5 million light-years from the Milky Way and is actually moving toward us, not away. Local gravity wins at that distance. The solar system is not expanding. The Earth is not slowly drifting away from the Sun. Everyday experience is not distorted by cosmic expansion, and the expansion is not something you would ever feel or measure at human scales. But at the scale of galaxy clusters and beyond, at distances where local gravity can no longer maintain its grip, expansion takes over. The boundary is not sharp, but the transition is real. Beyond roughly 5 to 10 megaparsecs, the expansion of space dominates over gravitational attraction, and galaxies that are not gravitationally bound to each other recede. At distances large enough that recession speed exceeds light speed, photons from those galaxies spend their entire journey in expanding space. The expansion is faster than the photon can traverse. They never arrive. The consequence of accelerating expansion is not abstract. At this moment, galaxies more than 14 billion light-years away are receding from us faster than light. This is not an approximation or a rounding error. It is the current state of the cosmos. Those galaxies are not moving through space at superluminal speed. They are stationary in their local space, just as we are stationary in ours. But the space between us and them is growing faster than any light beam could traverse it. Any photon those galaxies emit right now is headed toward us, but the space ahead of it is expanding faster than the photon can cross. The photon will never arrive, not ever. Those galaxies are communicating their past to us, old light from when they were closer, still making the crossing. Their present and future are permanently sealed off. We can still see them, for now, as echoes. Their current state is already unreachable. This is not a future crisis. It is the current geometry of the universe. How does a galaxy disappear? Not with a blink, not abruptly. The process is gradual enough to be invisible on any human timescale, but it is physically precise. As a distant galaxy recedes faster and faster, the light it emits gets stretched. The wavelength of light stretches as the space it travels through expands. This is the cosmological redshift, the same process that made the expansion detectable in the first place. A galaxy moving away quickly emits light that arrives redshifted toward longer wavelengths. As the recession speed increases, the redshift increases. The galaxy dims. Its light shifts out of the visible spectrum into the infrared, then into the radio, then into wavelengths too long for any instrument to detect. The galaxy does not blink out. It fades. It shifts. It dims past the detection threshold of any possible telescope. And then it is gone. Not destroyed, not moved. Still there in its own space, permanently beyond the reach of any information we could ever send or receive. The Hubble constant measures the current rate of expansion, how fast space is growing per unit of distance. Different measurement methods have produced slightly different values. The discrepancy between them is one of the outstanding problems in modern cosmology, sometimes called the Hubble tension. The expansion rate determines when galaxies crossed our horizon in the past, how quickly more are crossing it now, how long the window of full cosmic observability will stay open. A higher expansion rate means the horizon is closing faster. A lower rate gives more time. The answer is not yet settled, and the uncertainty is not trivial. But both possible answers agree on the direction. The window is closing. The only open question is how quickly. The observable universe is not a fixed region. It is a boundary defined by light travel time, the distance light has had time to cross since the Big Bang. That boundary currently sits at roughly 46 billion light-years. But the boundary of what we can still receive new information from is smaller and shrinking. Galaxies are crossing that inner horizon constantly, sealing their futures from our observation, one by one, on a timeline determined by dark energy. The observable universe, as a fraction of the total universe, is getting smaller, not because the total universe is shrinking, because the rate of expansion keeps pushing more of it beyond the horizon before its light can reach us. There is also a version of this that is already operating, not just in the future. Right now, Roughly 94% of the observable universe's volume is already beyond the region from which we could ever receive a reply to any signal we sent. If we transmitted a message tonight toward a galaxy 15 billion light-years away, it would travel at light speed. The space ahead of it would expand faster than it could cross. The message would never arrive. The galaxy would never know we existed. Not because of distance, in the ordinary sense, because the medium between us is expanding at a rate the message cannot outrun. Intergalactic contact, any physical exchange of signals, any communication of any kind, is already foreclosed for the vast majority of the universe. Not eventually, now. Already closed. The galaxies we can still theoretically reach with a signal are a small and shrinking subset of what we can see. We are already, right now, more isolated than the night sky suggests. The visibility of those galaxies is a record of their past. The possibility of contact is already closed. The obvious counterproposal is technology. If expansion is the obstacle, engineer around it. Warp drives bend local space. Wormholes create shortcuts through it. General relativity permits, in theory, geometries of space-time that could allow travel across distances that straightforward motion cannot cover. Could an advanced civilization chase the receding galaxies? No. The reason is geometric, not engineering. Local space manipulation works by altering local geometry, bending spacetime near a ship, creating a bubble of compressed space ahead and expanded space behind. It does not alter the global expansion. The expansion of space is a property of the universe at cosmological scales, not a local condition that can be overridden with sufficient cleverness. More critically, the expansion gets faster the farther away you go. A galaxy 20 billion light-years away is receding faster than one 14 billion light-years away. A galaxy 50 billion light-years away is receding still faster. The target is not just retreating, it is retreating at an accelerating rate. Any shortcut faster than light still needs to cover a distance that grows faster than the shortcut can span. The problem is not your speed, it is the geometry. The destination is receding on a curve that no finite speed can match at these scales. The geometry of the universe does not provide an exit from this. There is a final implication to this that is harder to look at directly. In roughly 150 billion years, every galaxy outside the local group will have crossed the horizon. The local group is the small cluster gravitationally bound to the Milky Way, including Andromeda. The sky will contain one galaxy. The Milky Way and Andromeda will have long since collided and merged into a single elliptical structure. Beyond it, nothing visible. Not dark, exactly. The stars within the merged galaxy will still burn. But the broader universe, the billions of other galaxies that exist right now, will be gone from view. Completely. Permanently. Any civilization alive at that point will look out at a sky containing only their own galaxy. They will draw the obvious conclusion. This is the universe. One galaxy. Alone. They will be wrong, but they will have no way to know it. The redshift of distant galaxies allowed Edwin Hubble to establish the expansion of the universe in 1929. That redshift will eventually shift into wavelengths too long for any instrument to detect. The cosmic microwave background was discovered in 1965 by Arno Penzias and Robert Wilson, the oldest light in the universe, still arriving from every direction at 2.7 Kelvin. It will redshift into wavelengths below the detection threshold of any possible receiver as the universe cools further. The supernovae that told Perlmutter and Reese the expansion was accelerating will be too far away and too redshifted to resolve. Every piece of observational evidence that allowed cosmology to reconstruct the universe's history will cross the horizon or fade below detectability, over timescales of tens to hundreds of trillions of years. A civilization arising late enough will not discover dark energy. It will not measure the expansion. It will not detect the Big Bang's afterglow. It will do impeccable physics on an apparently static, single galaxy universe. Its conclusions will be internally consistent, completely wrong about the larger reality. Not because it failed, because the evidence expired before it arrived. We are in the privileged era. The current cosmological moment is the only era from which the full architecture of the universe is observable, a window of a few tens of billions of years around the Big Bang. The galaxies are still close enough to detect. The expansion history is still readable in their redshifts. The cosmic microwave background is still present and measurable. The structure of the universe, its origin, its composition, and its fate are all still available to observational science. That window is open right now. It will not stay open. It is closing on a schedule set by dark energy and measured in the recession speeds of galaxies we can still see tonight. The night sky looks fixed. The constellations are where they were last night and where they will be next year. Nothing in a human lifetime or 1,000 human lifetimes moves visibly. The horizon is expanding on timescales that make civilization look instantaneous. But the direction is set, and the mechanism is running. Every second, light from a galaxy that crossed the permanent horizon is the last light from that galaxy that will ever arrive. The galaxy continues to exist. The space between us simply grows without bound, in silence, at a rate that nothing physical can match. The universe is most visible right now, from this moment in cosmic time, from this planet, looking up at this sky. That will not be true forever, and there is nothing to be done about it.